So before we do combinations and compositions of trig functions, we're going to first review combinations and compositions without trig functions. So this is something that we learned earlier this year. We also learned it in Algebra 2. All right, so first we're going to go over a combination. Now, a combination is when you take two functions and either add, subtract, multiply, or divide. This is a combination. You're combining two functions together. Versus a composition is when you put one function or multiple functions into another. Whoops. And we say compositions, so composition, by saying f of g or g of f. And it's used with this like small open dot, f of g. All right, but first let's review a combination. Here we have two functions where it wants us to multiply these two functions with the initial input into both of -1. So what this means is we need to take -1 and input it into both functions and then multiply them together. So what I'm going to do is I'm going to take each original function and I'm going to write them right next to each other like I was going to multiply them together. But before I multiply them together, I need to address this initial input. I need to input -1 instead of t. So wherever I see a t, instead of writing t, I'm going to write my input of -1. And then I'm going to simplify first. PEMDAS tells me to deal with the parentheses first. So I'm going to have -1 squared, which is 1, plus 3, which is 4. And then I'm going to have 4 times -1, which is -4, minus 3 is -7. 4 times -7 is -28, meaning g times h of -1 in total is equal to -28. And I'm done. That's a combination. Hopefully this is ringing some bells. Hopefully you're like, oh yeah, I remember that. I forget what unit it was. I think 2? I think we did this in unit 2. Sinusoidally. Is it really? I need to get a new headset. I'm sorry. Hopefully it gets better. I think it's this mic. I think I keep like looking down and then looking up and maybe it's like not. Do I need to go like this? Can you hear me better now? I really don't want to sit like this. I'll go like this. Okay. No, I won't. Hopefully it gets better. All right, so now we're going to review a composition, which is where we are taking one function and inputting it into another. Now, when we have a composition, there's two ways to write it, right? Let me erase this and put g of f because that's what this example is telling us. So either it can be written as g parenthesis f parenthesis and then whatever your initial input is. Or you can write it as g and then that open dot of f and then your initial input. So this open dot means composition. That's what that means. We're inputting the second function into the first function. Now, I like looking at it in parentheses terms because I think that it makes more sense in my head because we know that we're looking at the innermost parentheses first. So my innermost parentheses are 2. That's my initial input. I'm taking that 2 and I'm inputting it into the very next letter outside of those parentheses, f. So first thing I need to do is input 2 into F. Uh-oh. Uh-oh. Something is failing. So we're inputting, what are we putting? Inputting 2. So we need to solve for f of 2 first. We have 2 squared, which is 4, times 2 is 8, plus 5 is 13. So we're taking this first output and we are treating it as the input into the letter outside of our f. So we're inputting this f of 2, which is actually 13, into g of n. So now, instead of writing n in g of n, we're going to be inputting 13. Oops. So then we have 3 times 13, which is 39, plus 2, 41. So g of f of 2 is equal to 41. And we're done. Are there any questions on either combinations or compositions so far? Again, like I said, hopefully you're recalling some of this. Hopefully. Now, what we're going to do is we're going to take this concept and we are going to use trigonometric functions instead of linear and quadratic, which is what we were just using. So instead of linear and quadratic, we will now just be using trig. Now it is, I didn't bring it with me. I don't have my unit circle with me. I'm a bad student. It is extremely useful to have your unit circle out in front of you. Very useful to have it out in front of you because I don't know about you, but I have not memorized all of the trig values for every single angle on that unit circle. All right, so I'll do one combination and one composition. Let me see, I don't think I want to do the easiest one. Let's do number 5 as our combination. So here we have f over g of 5 pi over 6. Now, this is not a composition, so we're not inputting 5 pi over 6 into one of these functions. We're inputting 5 pi over 6 into both and then dividing them. That's the combination occurring here. So I need to figure out what my f function is, and all 4 are listed right up above. So f of x is sine of x. I'm going to write that down here so I can look at it easily. F of x is sine of x, and g of x is cosine of x. Now I need to take both of these functions and input 5 pi over 6 into both. So this whole thing actually equals sine of 5 pi over 6 over cosine of 5 pi over 6. All right. So now these are different functions, just like a linear is a different function than a quadratic, okay? They're totally different functions. I can't just divide them. What you do instead is you have to find their values. So we know 5 pi over 6 is a angle on the unit circle. And I also know that sine is the y value and cosine is the x value. So if I'm trying to find sine of 5 pi over 6, all I need to do is look on my unit circle for the angle 5 pi over 6 and find the y value. So you guys are going to, yes, you're right, Arnon. So you guys are just going to have to help me out here because I don't have the unit circle in front of me. What is the y value of 5 pi over 6? 1/2. Okay. So I know that the numerator here is a half. What is the x value of 5 pi over 6? At the angle 5 pi over 6, what is negative? Wonderful. That seems right to me. So now we can't leave it like this. We know we can't leave it like this, right? This is a fraction inside a fraction, or two fractions inside of a big fraction. In order to simplify this big fraction, what do we have to do? Exactly. You multiply the numerator times the reciprocal of the denominator. So now we're multiplying fractions. Whenever we are multiplying fractions, just like when we were doing those great big long conversions with all those conversion fractions, if we have a like term between the numerator and the denominator when multiplying, we can cancel. So here I have a 2 and a 2. One in the numerator, one in the denominator. They actually cancel each other out, right? 2 divided by 2 is 1. So my answer here is actually a negative 1 over square root of 3. But, once again, we cannot leave a square root in the denominator. So we're going to multiply this by the square root of 3 over the square root of 3. And we end up with negative square root of 3 over 3. That is our end result. Are there any questions on this combination? No, no, I think that's fine. I would, if this was me, I would just circle that. That is my answer. Right, right. Yeah. Oh, that too. Yeah, right. You're not writing anything. Yeah. Oh, gosh, what a mess. All right. So now I'm not going to do this one. I know you're looking at this like, "Oh my gosh, I wish you would." However, I honestly don't think that you have one quite this difficult on your test, so I don't want to do one quite this difficult in the notes. Now, if I do come across one this difficult on your test, I will go back and do this, but I honestly do not remember. All right, I lied. I will do this one. Jesus, that is a composition. All right, so we're going to do this one. Now, this is a composition. The reason I know it's a composition is because we literally have a function inside of another function. Now, the innermost parentheses is my initial input. So what I need to do first is take pi over 4 and input it into g, which what was g? Cosine of x. So I'm inputting pi over 4 into cosine of x. So that means instead of x, I'll write pi over 4. Now, someone help me out here. Well, I do know this one. This one I do have memorized, but I'll pretend I don't. Help me out. What is the cosine value of pi over 4? Exactly, yes. Pi over 4 is that 45-degree angle. I know for sure that that coordinate point is square root of 2 over 2 comma square root of 2 over 2. So here, the x value of cosine of pi over 4 is square root of 2 over 2. So this is the value that I'm taking and inputting it into the next function outside of that parentheses, which is z, and z is x squared. So I'm taking the square root of 2 over 2 and inputting it in for x into my z function. Now anytime I'm squaring, what I'm actually doing, we should know by this point, what I'm actually doing is multiplying the number by itself. And we should also know that anytime we're multiplying a square root times itself, it is the number on the inside of the square root. And also, I kind of skipped over saying this, but when we're multiplying fractions, you multiply the numerators and you multiply the denominators. So I multiplied square root of 2 times square root of 2 and it got 2. And then I must multiply 2 times 2 and get 4. And that simplifies down to a half. So that is my answer. Are there any questions on this composition? Are there any questions in general on combinations or compositions? Any of these that you think that you wouldn't know how to solve? Exactly. Yes. Anybody else? I will write if you're curious, I will write the answer, or I'll solve the problem on the key if you want to look back at how to do it. But really, this is not, if you're really looking at this problem, it's not that tricky, right? It's just a composition and a composition. And once you find the two answers to those compositions, you're subtracting them. So what? You know, it's like two problems in one. Okay, we can do that. But again, we won't do that to you on the test. All right. So now on to the somewhat new part. Somewhat. Um we're not asking you to do anything that you haven't done before. What's different for us is normally I show you my little graphing calculator, right? Well, to look at these combinations, instead of graphing it on my graphing calculator, what I'm going to do instead is I'm going to show you it graphed on Desmos. And the reason I'm doing this is because, like I said before, from now on, it wants all of your answers in terms of radians. And you may have noticed that your graphing calculator gives you the x values as not exact answers, as decimals. So instead of keeping it in terms of radians with that pi symbol, it instead gives you a decimal. And unless you have all of the angle measure decimals memorized, it's going to be really, really hard for you to look at your graphing calculator. So instead, it's much, much, much easier to look at Desmos instead. So what we're going to do, I probably will only have time for the first two, to be honest. I kind of want to have time to talk about number 4 just because of this dampening factor. It's not going to be quizzed or tested over. It's actually a concept that is more heavily used in calculus. But, I mean, it is good to let you know what it is. But if we don't have time for number 4, it's not a big deal. It's not on your quiz. It's not on your test. It's not a big deal. So hopefully we'll have time for 1 and 2, and then maybe for number 4. And right up here where it says use a window of, this is if you're using your graphing calculator, which we're not right now, so this really doesn't matter because on Desmos you can zoom in, zoom out as much as you want. All right, so let me go to my Desmos. Let me open this up. Let me go to my Desmos, and I am going to be typing in that first function. So let me move this over. Okay, so we're going to look at this on Desmos first. Y equals 2 times, which hopefully you guys have been using Desmos in some fashion and realize that it is easy to use. I am just not used to it. I'm old school and I always use a calculator. So I'm learning Desmos. All right. So this is our function. Now if I zoom in, why won't it let me zoom? Guess I have to zoom like that. All right. So if I zoom in, it's fine for right now that our x values are whole numbers. However, if you want to look at this x-axis in terms of radians, all you have to do is go over here to this wrench symbol, click it, and then where it says x-axis and it says step, just type in pi, and it converts your x-axis into radians. Honestly, this really doesn't matter too much because even if you hadn't put that, so let me take it away, and we were trying to figure out where this 0 is, and you click on it, it gives you the x value in radians already. But I like to look at it in terms of radians. It makes my mind cooperate more easily. All right, so here we go. This is our function. Let's answer the questions on our notes about this function, about this combination, really. So our domain, our domain for this function, I already gave you the answer. I can't believe I said it, is what? What is our domain for this function? Should we pull up Desmos? You don't need to. No, we can just look at my Desmos. That's fine. But what is my domain? If I scroll outward, oh, it's annoying me that I can't use my fingers. What's my range? I'm sorry, domain. All real numbers. Thank you so much. Now I have to zoom way back in. Okay. So here in our notes, we're going to put x is an element of all real numbers. Sorry, my handwriting is going to be kind of awful right now because I have my laptop like actually up as a laptop. What is my range? Yes, exactly. We actually have values, y values of -3 and 3, so we use those brackets. Wonderful. It's -3 to 3. Now, what is an extrema? Exactly. Yes, they are any extreme points that are higher than the points surrounding it or lower than the points surrounding it. Now, there are two different types of extrema. There are local extrema, and then there are absolute or global extrema. We don't have an absolute maximum at all. All that we have are infinitely many local max and mins. Oh, exactly. Yes, Arnon. So here, what we can say is that we have local maxes at y equals 3. And we have local mins at y equals -3. Infinitely many, but that's where they're located. So here, extrema, we say local max at y equals 3 and local min at y equals -3. End behavior. What would you say the end behavior is for this function? Yes, Garrison, exactly. Remember, we ask ourselves about end behavior by asking, as x approaches infinity, what happens to your y values? Well, as x approaches infinity, as it gets larger, y goes up, and then it goes down, and then it goes up, and then it goes down. It's never approaching a specific value. So here, we say none. There is no end behavior. What about our zeros? Oh, now it lets me touch it. So here I can see, and I love Desmos because on our graphing calculator, we would have to put this into y equals, and then we'd have to hit second trace, and then we'd have to hit zeros, and then we'd have to do that whole, left bound, right bound guess, left bound, right bound guess to get both of these. Whereas on on Desmos, you can just click the point and it gives it to you. So here we have a 0 at pi over 6. We have a 0 at pi over 2. What is happening here? How can we say where these zeros are located? Instead of listing every single one, what can we say instead? Right, well, you're close. Right, Caitlin, yes. What we do is we take one of these. It doesn't really matter which zero we state, but I'll state this first positive 0 of pi over 6. We take pi over 6 and we either add or subtract, because actually each and every time we're increasing or decreasing by pi over 3, and it's any multiple of pi over 3. So we can put an n. So what this means is, if I'm looking at my Desmos, what this means is if I take pi over 6 and I add pi over 3, I get pi over 2. If I take pi over 6 and add 2 times pi over 3, I have 5 pi over 6. If I take pi over 6 and add 3 pi, I'm sorry, what was I saying? No, 3 times pi over 3, I would get 7 pi over 6. And you can do the exact same thing, but subtracting instead. So this expression, pi over 6 plus or minus pi over 3 times n, gives you every single zero. Are there any asymptotes on our graph? Oh, there we go. No, there are no asymptotes. There are no asymptotes. Whoops. Okay. So these, I don't know if you noticed, but I did skip over answering two things earlier in our notes. How do you know if a function is a sinusoid, and how do you know if a function is periodic? So if you recall, when we were going over graphing, a sine wave is a function that is a sinusoid. It has the shape of a sine. So if I'm looking at a sine graph, this is my parent function, right? Anything that shares that same shape is called a sinusoid, meaning a cosine is also a sinusoid. All that you need to know about a function to determine if it is a sinusoid is if your two functions in your combination have the same b value. The function produced will be a transformation of sine parent function. And then also, if a function is periodic, what that means is it endlessly repeats the same values on regular intervals. So just like we know that a sine has a single period for the length of a single wave. So if something is periodic, it takes that single period and repeats it over and over and over again, making it periodic. So we can say here a function that repeats its values in regular intervals is periodic. So the only way to know if something is periodic, well, it's not the only way, but the easiest way to know if something is periodic, what the heck was I spelling? Is to look at its graph. If we look at its graph and we see that it is repeating endlessly, no, Anna, not necessarily. But okay, so I see where you're going with that. If something has the same b values, then guaranteed it is a sinusoid, meaning it is periodic. But functions that don't share the same b value can still be periodic. Oh yeah, we will. Yes, no worries. So these are our two definitions. On the example we're working on here, first I'm asking, is it periodic? So let's look at the graph. Are my values repeating over and over and over again? Yes. Clearly we can see that it's repeating the same period over and over and over again. Also, we can clearly see that this is a sine wave. I mean, it has the same shape as a sine wave, meaning it is a sinusoid. Now, we could have either looked at this graph and known this, or if I'm looking at this function, my first function inside the combination has a b value of 3. My second function inside the combination also has a b value of 3. These being the same means that this is definitely a sinusoid. So there's two ways you can figure out if it's a sinusoid. Look at the graph or look at those b values. So is it periodic? Yes. The values repeat. And is it a sinusoid? Yes. The graph is a transformation of sine. All right. So that's basically all that you need to know. All of the rest of these problems, when looking at Desmos, we ask the same questions. Yes, they'll look different. So before we leave, let me just show you what the second one will look like. We have cosine of x minus sine of 2x. Cosine of x minus nope, what the heck am I writing? Okay, so this is this function. So let's just talk about it super quickly. Is this function periodic? It is, but is it a sinusoid? No, for sure not. So this is what I was saying by something can still be periodic, but not a sinusoid. Something cannot be a sinusoid and not periodic. If it is a sinusoid, then yes, it is periodic. I hope that that makes sense. Um, Also the hardest, okay. The hardest part about this problem, I think, is understanding how to write the zeros. So let's just talk about it super, super quick. If I am looking at this graph, like this pi over 6 is the start of a period, this would be the end of the period, right? So here are all my zeros. How I would write these zeros is, if I'm looking at this first zero, these zeros are all equal distance from each other, right? Meaning, if I take pi over 6 and add a certain amount, I can get the other three zeros that I have circled. Now, how much do I add to pi over 6 to get 5 pi over 6? How much do I add to this to get this? Right, 4 pi over 6, which simplifies to 2 pi over 3. Exactly. So, to get most of the zeros, oh boy. Oh, well, it's okay. These are the other notes from third period, but we can just use them. To get some of the zeros, if we take pi over 6 and add or subtract 2 pi over 3, we can get most of the zeros. However, I'm looking back at this graph, I still have not accounted for this zero. So, this 0, pi over 2, what statement could I write to include this 0 and every 0 in any of the other periods? This is the next one that corresponds to pi over 2. I guess I wrote right over the... This is located at 5 pi over 2. What did we do to pi over 2 to get 5 pi over 2? Yes, what does that simplify to, Arnon? 2 pi. Yeah. All that you do to pi over 2 to get all of the corresponding zeros to pi over 2 is add 2 pi. So here in our notes, if we say pi over 2, if we add 2 pi n to pi over 2, we will get all of those corresponding zeros as well. So that was the hardest part. I don't know that you're going to do anything like that on your Math Excel, but I did want to show you just in case you do. Are there any questions from today? Oh, I went 6 minutes over. I'm so sorry. I guess I talked too much in the beginning.